All right, in this video, we're going to introduce and use the squeeze theorem. The squeeze theorem is going to be a nice result that we'll be able to use to evaluate some tricky limits that don't fit some of the previous kind of forms that we've seen. It's going to be based on bounding our functions above and below, getting some inequalities. And so one of the big questions that students will ask a lot when using the squeeze theorem is, how do we find those appropriate bounds? So we'll talk about some situations there, and then obviously we'll try and talk about when it might be helpful and some other notes about it. But first, let's just start off with figuring out what the squeeze theorem actually is. So assume we have these functions, f, g, and h, three different functions that satisfy this inequality. So we have a small function, a middle function, and a big function here. And this is bounding the y values. And this is true for all the x values around a, again, except possibly at a itself. Hopefully that makes sense why we put that in there, because limits don't care about what's happening at that x value. So the theorem says that if we have this ordering of functions, if the small function's limit as x approaches a is equal to the big function's limit as x approaches a, then that means that our middle function has to be the same thing. So you can think of things this way visually. We've got some small function, we've got some big function here, but at this point, they approach the same thing. That means this middle function that might be bouncing around has to get squeezed in between there. That's why we call this thing the squeeze theorem, or sometimes you'll hear it called the sandwich theorem, because this middle function gets pinched in here at that x value of a, or at least as we're approaching it. Again, we might have like a point defined way down here, but that doesn't really matter. We just care about what's happening as x is close to a. All right, so what we need to do, though, is have this boundary of functions, right? We need to have this inequality right here. And this is a tricky thing. We have to have three functions when we're only given one. We only care about the limit of g. We have to come up with f and h. They have to be functions that fit this boundary, and the limit needs to be the same thing. So sometimes we'll just be given those bounds. We'll be given three functions to work with. We'll be told that they fit this inequality, and we'll be able to apply the squeeze theorem from that. That's going to be the first example that we start with. Sometimes we can get a visual representation of the functions to try and find these things. If we can create a picture like this and convince ourselves that they have this kind of ordering, that's okay. But the more analytical or formal version of this is when we actually build that inequality ourselves, using some knowledge of the functions we're given. That's obviously going to be trickier to do because we have to know a lot about the function we're working with. So here's an example where we're just given this boundary, right? We're given three functions. I'm going to tell you the negative absolute value of x is less than or equal to cosine x minus 1 over x, and that's less than or equal to the positive absolute value of x for all the x values that aren't 0. Obviously, you can see what the problem is when x is equal to 0. We're going to divide by 0, and things are going to get all wonky. But we don't care about that because x is just approaching 0 here. So first, let's go ahead and set this inequality up. We've got that the negative absolute value of x is less than or equal to cosine of x minus 1 over x, and that's less than or equal to the absolute value of x for x not equal to 0. And if this is true, that means that these limits have to have the same ordering. If this is true for all the y values, or for all the x values, that are close to 0 or not equal to 0, then it has to be true for all the x values that are close to 0. So we get this ordering of limits. This is our f function, this is our g function, this is our h function. We don't care about the names, we just care about these inequalities. Now what we need to do is figure out this limit. What you'll notice is that we can just bring this negative outside. So once we know what this limit is, underlined in red, then we suddenly have the limit over here. And hopefully they're the same thing. So let's find this limit. The absolute value of x is a piecewise function. It's negative x if x is less than 0, and it's x if x is greater than or equal to 0. You've probably seen this before. And so what that means is that we can take a look at a left-sided limit and a right-sided limit here. The limit as x approaches 0 on the left of the absolute value of x, that's going to be when x is less than 0. So we're going to use this rule for our function. That's the same thing as the limit as x approaches 0 on the left of negative x. Now, this is a tiny, tiny, tiny polynomial function. right? It's a single term. It's really just linear, negative x. But we found that polynomial functions, their limits are really nice because you can just plug in the x value. And we found that that worked even for one-sided limits. So this is really negative 0, or just 0. Similarly, we can do the limit on the right of this absolute value function. And we'll find that as we look at the absolute value function on the right of 0, we're looking at x values bigger than 0, so we'll just use our regular x. And so this is just 0. I guess I don't need to write 0 equals 0, that's kind of silly. But what we're finding is that the left side limit and the right side limit are both the same thing. That means this limit is equal to 0, and that means this one is negative 0. Oh, that's 0 as well. Okay, so let's write this out again. So we're really saying that the limit as x approaches 0 of the negative absolute value of x was going to be less than or equal to the limit as x approaches 0 of cosine of x minus 1 over x, and that's less than or equal to the limit as x approaches 0 of absolute value of x. But we found what both of these were, right? We said that both of these were equal to 0. So what the squeeze theorem says is that this limit that we care about, that we don't know really anything about, this limit as x approaches 0 of cosine of x minus 1 over x, is really bounded in between 0 and 0. So we don't know anything about this limit, but we do know that it's a number between 0 and 0. Well, okay, so that means we know everything about it, right? Obviously, then, this limit has to be 0. There's only one number that's greater than or equal to 0 and also less than or equal to 0. It's when they're all 0. So you can hopefully see why we need those two outside limits to be the same. If we had some boundaries where this limit over here was negative 1 and this limit over here was 5, all we would know is that the limit we cared about was between negative 1 and 5, which maybe is useful. But it's much more useful when we can get this to be bounded in between a number and itself. All right, so let's do the same thing, but here we're going to notice that we don't have boundaries given to us. What we're going to do is investigate these graphically. So we'll pull up a graphing calculator. I'm going to use Desmos, and I'm just going to plot some functions that are greater than this blue curve and less than this blue curve. And we specifically care about what's going on around 0. So greater is pretty easy. We can just say y equals 1. There's our upper bound on this, right? And I can zoom in on this thing, and I'm pretty clear that this is going to be a nice upper bound on our function. I also might notice that we have this kind of curviness in the middle that kind of looks like a parabola. So I'm going to use an upside down parabola here. But you'll notice that this doesn't work out nicely because we want it to get squeezed, right? So let's go ahead and shift this thing up 1. And now if we zoom in, we hopefully are going to be convinced that yes, this blue function is actually in between our green one and our purple one around this x value of 0. Hopefully that's enough evidence for us to be convinced. So what we've just done is we've said that this sine of x over x function is bounded in between the constant function 1 on top and the parabola negative x squared plus 1 on the bottom. And this is true for all the x values that aren't 0. Again, we can't look at the x value specifically at 0 because we're dividing by 0 here. So as long as you're not looking at 0, this is true. We really only need it to be true for the x values around 0, but if you zoom out, you're going to notice that everywhere on this curve, our blue function is in between the purple one and the green one. So that's pretty cool. Okay, so what we want to do now is apply a limit. If this is true for all the x values that aren't equal to 0, then it's got to be true for the x values that are just close to 0 but not equal to 0. So that means the limit as x approaches 0 of negative x squared plus 1 is less than or equal to the limit as x approaches 0 of sine of x over x, and that's less than or equal to the limit as x approaches 0 of 1. And what you'll notice is that these two limits are nice and easy, right? This one over here is just 1 because this is a constant function. And this is a polynomial, meaning you can plug in 0 for x, and we get 0 plus 1. So what we found, again, is that our limit that we don't know anything about, but we want to know about, is stuck in between two numbers, 1 and 1. So again, we're pretty convinced that this limit has to be 1. The only value in between 1 and 1 is 1. That's kind of a silly thing to say, but that's what the squeeze theorem does. All right, in our last example, what we're going to do is we're going to build these bounds analytically. We're going to do it by ourselves here. And what we're going to notice is that we know some boundaries for a cosine function. I know that cosine of theta is stuck in between 1 and negative 1, right? If you think about a unit circle here, we know that cosine is always going to be the x value on the circle. And so we are stuck in between these two x values, negative 1 and positive 1. So if that's true, then what we'll do is we'll just say, all right, let's let theta be 1 over x. Suddenly, what we have is that cosine of 1 over x is stuck in between 1 and negative 1 as long as x isn't 0. Because again, if x is 0, we get all screwy. This division by 0 is going to mess us up. But that's fine. We're only looking at what happens when x approaches 0. So that's cool. We'll also notice that this function that we're bounding is not the function we care about. What we care about is x to the 4 times cosine of 1 over x. So what we can do is just go ahead and multiply x to the 4 on each part. You might remember that with inequalities, when you multiply positive terms, you can just multiply on each side of the inequality. But when you multiply or divide negative things, you got to switch the order of the inequality, right? Notice that x to the 4 has to not be negative. In fact, it has to be positive here because this is happening for the x values that aren't 0. So we have this even exponent. We're multiplying a number by itself an even number of times. It has to be positive or 0 if x was 0, but we're told x isn't 0. So this has got to be positive all the time. So that's nice. So what we have now is negative x to the 4, that's negative 1 times x to the 4, is less than or equal to x to the 4 cosine of 1 over x, and that's less than or equal to 1 times x to the 4. And here's our inequality that we can use on our next page when we start evaluating this limit. So this is the inequality that we've built. Now we can start applying the squeeze theorem. This is true for the x values that aren't 0. So what that means is that if we apply a limit as x approaches 0 here, it'll still be true. Because if it's true for all the x values that aren't 0, it's true for the x values that aren't 0 but happen to be really, really, really close to 0. Now, what you'll notice is that these two limits are super easy, right? Both of these are tiny little polynomials. You can just plug in 0 here, and we get that 0 is less than or equal to this limit, and that limit is less than or equal to 0. Or this limit, as x approaches 0, of x to the 4 cosine 1 over x, is stuck in between 0 and 0, and so by now we've figured this thing out. This limit is equal to 0 by the squeeze theorem. So that's what the squeeze theorem can tell us. We can use a version of the squeeze theorem to evaluate limits like this. Notice this is one of those ones where we get 0 over 0. We might normally just go ahead and factor things, right? We might normally say, well, wait a second, this numerator is x plus 1, x minus 1. And so if you do this like canceling out, you could see like, oh, really, we just care about this limit as x approaches 1 of x plus 1. That's just going to be 2. What you can say, though, is that x squared minus 1 over x minus 1 is less than or equal to x plus 1 and greater than or equal to x plus 1 for all x not equal to 1. In fact, what we can say is that they're equal to x plus 1 for all x not equal to 1. But let's just use this inequality stuff just so we can get used to it. This is kind of a weird, silly one. But now when we apply that limit, things go the exact same way that we thought they were going to. The limits on the outside are 2. So this limit as x approaches 1 of x squared minus 1 over x minus 1, it's got to be equal to 2. But again, we could just do that using that result that we had earlier that says, well, okay, we can find a different function that matches up with the function we care about everywhere except possibly at 1. And that's what we've got here. Okay, so when is this actually helpful? Why do we need to use this? This seems like a really, really big and kind of complicated to result to wrangle. It's really helpful when we're dealing with trig functions. You saw earlier that we were able to build an inequality with a trig function because we knew the range of the cosine function. So that's a really nice thing. If we see trig functions in there, we should start by thinking, well, I know that trig function, sine or cosine, is bounded between -1 and 1. That's the range of those functions. And then we can maybe build some inequalities from there. Later on, we're going to work with end behavior of functions, and we'll find out that it can be really helpful to do some squeeze theorem things in those kinds of cases. And then what we'll also notice is that when we work with new function types that we haven't analyzed yet, we're going to need some methods to find those limits until we build up some general rules for them. So when we start thinking about exponential functions and log functions and things like that, we might need some rules for limits that we can use. The squeeze theorem could be helpful then. A couple other notes. We started off by giving some inequalities to use, and that's going to be something that you'll see still. You'll be given some inequalities. That's mostly helpful to just build some intuition for how the squeeze theorem gets applied. But eventually we're going to need to come up with those inequalities ourselves. Getting those inequalities from pictures of graphs is not a formal way of doing it. It's not precise. You're using graphical approximations of those. You're looking and saying, I'm pretty sure that we have this ordering of functions. We're pretty sure that as we get close to 0, the green function is on top and the purple function's on the bottom. Pretty sure isn't good enough technically, but it can be really super helpful for building up some ideas for how this goes. That's the squeeze theorem. When we move on from this, we're going to start talking about limits that involve infinity, whether it's the y values going off to infinity or the x values going off to infinity. So that's what we've got up next.